Welcome to Chapter 13 in our exploration in the solar system, except this time we're going to be looking outside of our solar system. We're going to be looking at exoplanets. And guess what? When I was taking Astronomy 101, this entire chapter didn't exist. It wasn't until 1995 that we confirmed the first time we found a planet around another star. When I was taking this class back in 1983, we had one sentence in one paragraph that said, maybe someday we'll know whether or not there are planets around other stars, but as of yet, we have no idea. My, how things change. Now we have not only an entire chapter in your class, but you can get an entire graduate degree in exoplanets. So we have learned a lot, we have discovered a lot, and this is a great time to be doing astronomy. So I invite you to follow with me as we look at exoplanets, which is planets outside of our solar system, and see what we might be able to learn about them from what we know about our planets and what we can learn from them to better understand our own. So let me figure out here how to share the screen again. There we go. And you can see my backdrop there. Let us go to play from start. It is hard to find things out about exoplanets because they are very, very far away. When we're talking about the moon, it's 250,000 miles away. When we talk about anything within our solar system apart from that, they are millions of miles away, tens of millions of miles away, sometimes a couple of 100 million miles away by the time we're getting to the outer planets and out into the Kepler or the Kuiper belt. We're going to be getting into the billions of miles, but these, no comparison. These are trillions upon trillions upon trillions upon trillions of miles away, so much so that we can't even talk about them meaningfully in terms of miles. We talk about them in terms of light years. So we're going to be seeing things that are very, very, very far away. When we're looking at a star, most of the time what we're seeing is the light from the star, and it is so bright that it overpowers anything that might be in its general vicinity. We can see that happening in the daytime. Our sun is out, so nothing else in the sky, none of the planets, none of the stars, nothing else, with the exception of the moon, can be seen during the daytime. But that's not just a factor of the star being bright, but also the atmosphere. However, if you were to try to look at our solar system from the nearest star, which is Alpha Centauri, Proxima Centauri, a little over 4 light years away, and you had standard binoculars or even a standard telescope, you would not see any of the planets around the sun because the sun is so bright by comparison, and the planets are so dim and close by comparison, you wouldn't be able to see them. If you look at Jupiter, and if you're watching this video when I'm making it in the summer of 2020, then you could go out and look at Jupiter tonight. You can look at it with the naked eye and you'll see one dot. If you look at it even with low power binoculars, though, those dots spread out. I've talked about this in earlier lectures. That is because Jupiter is brighter by far than its moons. So the light sort of grabs together. The light coming off of Jupiter overpowers the others, and they all blend together. But when you magnify it, that separates out. When we're looking at stars, they are much, much, much brighter than the planets around them than Jupiter is relative to its moons. They're also much, much, much further away from us. So we had to wait really until the era of Hubble and other types of telescopes of that power, as well as various adaptive optics, to be able to see what we're seeing. Now, the idea that stars out there are other suns is nothing new. Christian Huygens, who was a telescope inventor and refiner in the generation right after Galileo, figured out that the same kind of light that's coming off of stars is coming off of the sun, only the sun is a very, very bright star close up to us. And the stars are suns very, very far away. You know, you take a light bulb and the further away it gets from you, the dimmer it appears, even though it's the same brightness. If I have a 100-watt bulb right in front of my eyes, I'll get sort of that sort of flash bulb effect. But if I have a 100-watt bulb a mile away, I probably won't even be able to see it because it's too far away. Christian Huygens lived in a time before photography, but he had what we would call a photographic memory. He would go out and look at the stars at night and then come back during the daytime. Don't try this at home, by the way. And he had this brass plate drilled with different sizes of holes, and he would hold it up to the sun and say, oh, that looks like Aldebaran, and that one looks like Sirius, and that one looks like Polaris. And he sort of figured out that the light is the same, only they're very far away. And if they are very far away, they could be the same size as the sun, and they might have planets like the sun. Now, if they were at very, very great distances, they'd also lack that parallax trick. Remember, I told you much earlier in the course, sort of close one eye and put your thumb up and then open your eye and things jump. The further away things are, the less they jump. Well, stars don't jump at all in that test. So Huygens said, yeah, right, because they're very far away. That's a further verification that that is the right answer. Huygens actually was commemorated on the Cassini probe that went to Saturn. As it was orbiting Saturn, it had a backpack thing that jumped off and landed on the moon Titan. I mentioned that in one of our earlier lectures, and it was named for Huygens. It was named for Christian Huygens here. Now, if we can't see the star with the planets around it, and there are a couple that we can, but 99% of them we can't, how do we know that something is around the star? Well, again, if we can see the planet itself around it, you take direct measures, we can take a direct picture. That's the best thing. But otherwise, we have to do indirect methods. So we have to figure out how the planets are affecting the star that we're seeing. And one of the best ways is a gravitational tug. Now, let's say my head is the sun, and my hand is Jupiter here, and my Jupiter is going around the sun like this. That's sort of the standard model of the solar system. But here's the truth. If the sun and Jupiter were both the same size, they would be going around each other. If the sun was larger, twice as large as Jupiter, then Jupiter would still be going around like this, but the sun would still be going around like this. It wouldn't be going around quite the same amount. It would be going around less, but it would still be wobbling back and forth as Jupiter went around. Well, Jupiter is large enough. In fact, our planet Earth is large enough, but Jupiter is the main planet, so Jupiter is the one we'd be looking for, is large enough that when Jupiter is here, the sun, remember my head is the sun, it's a little bit over here. And by the time Jupiter swings around over here, the sun is now over here. So as Jupiter goes around like this, the sun is actually going around like this, sort of going back and forth just a little bit. So even if you can't see Jupiter, if you're looking at the sun through your binoculars on Alpha Centauri, our nearest star, you're not going to see Jupiter with those binoculars, but you might see the sun sort of doing this, wobbling back and forth. Now it's going to wobble very slowly because Jupiter takes about 12 years to go around. So it's going to take 6 years, and then 12, then 18, and 24. So it's going to be a very slow wobble. The other planets also will cause it to wobble just a little bit less, and sometimes that'll smooth it out. But you'll be able to see the sun moving back and forth. That's called a gravitational tug. We can actually measure the sun moving around over the course of time based on Jupiter's mass, as well as all the others. All of our planets affect each other, but they affect them by very, very small amounts, because the further away you are, the less gravity will affect you along the way. So we can see that happening with our sun. We can see it happening with other stars. And that tells us that things are going around that. So this is an astrometric technique. We're sort of measuring what's happening with the astra, the star. So what we're doing is we're sort of watching it go back and forth. Now, stars are very far away, and they're also very tiny from what we see. So remember, the sky is 360 degrees. Each degree is broken up into 60 minutes. Each minute is broken into 60 seconds. Some of these wobbles back and forth are not even 1/10 of a second, 1/100th of a second. They can be 1/1000th of a second or less. Sort of, in fact, the twinkle of a star can cause more of a wobble than the actual star wobbling. That's one of the reasons why we've got to get up above the atmosphere for most of these kinds of measurements. That is important. That is important. So when we're looking at different kinds of probes that we've sent up there, we're trying to eliminate some of that effect. The Gaia mission from the European Space Agency can do this. The Kepler mission, on the other hand, was not looking for this. It was looking for something else. We'll talk about that here coming up. One of the other things that happens, we've talked about this before as well, if something's coming towards you, it has a blue shift. And if something's going away from you, it has a red shift. Remember those spectral lines when we're looking at the rainbow effect from a prism. And those lines will shift towards the red if it's going away from you. Those lines will shift towards the blue if it's coming towards you. Well, if the sun were wobbling because Jupiter was going around, again, my head can be Jupiter, it's not just going to wobble back and forth because Jupiter is going all around. So sometimes it's going to be coming towards you. Sometimes it's going to be going away from you. When it's coming towards you, it's going to get a little bit of a blue shift. When it's going away from you, it's going to get a little bit of a red shift. So a little bit of a kick in this direction, a little bit of a tug in this direction. So when we see the shift and shift, blue shift, red shift, blue shift, red shift, we can tell something's going around it, especially if we can then combine that with the wobble, 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 because that tells us that something's going around in a circle. Remember, all of this is three-dimensional as it's going around. We put those two things together and voila. If we're not seeing something doing this, because if it were another star, we would see it, it must be a planet. So the first verified planet that gave us this indication where the star was sort of wobbling back and forth and tug and pull in terms of the blue shift, red shift, was a nondescript star, not even one of the big ones like Sirius or Aldebaran or Polaris or Betelgeuse or anything like that. It was just the 51st star in the constellation Pegasus. So we call it 51 Pegasi because we're just that creative. We noticed that it had this wobble and Doppler effect going on. And we verified that this was happening over and over and over again. That's why you want to see it more than once, because if it's just going like this, it could just be going around something and then keep going. So you have to sort of watch it happen over and over and over and over again. Well, this one allowed us to do that because instead of going around once every 12 years like Jupiter, this planet whips around the star in 4 days. A year on this planet is 4 days long. Now that's not impossibly short, because 2 of the main moons of Jupiter go around Jupiter in less time than that too. Io and Europa both go around in less time than that. So we already have confirmation in our own solar system that that kind of orbital period makes sense, that can happen. So in 1995, this was verified. Now here's the deal. We'd seen a couple of planets around stars before 1995, but we didn't know what they were. We didn't know what we were seeing when we were seeing it. So we can't count those as the discovery. We just sort of count those now as accidental viewings along the way. We can't get an actual picture of 51 Pegasi's planet because it's too close to its star, and so the light blurs it out. But from the dynamics of what's happening, again, we can use those Newtonian equations. We can figure out that it's got a mass about the size of Jupiter. So we've got a Jupiter-sized planet right in close to the star, whipping around in 4 days. The star is also much smaller than our sun, which is why a big planet like a Jupiter-sized planet is pulling and tugging it as much as it is. So it would be inside the orbit of Mercury by a significant degree. That also makes it very hot. So instead of being out in the frozen land of our solar system where Jupiter is, it's in a place where we're getting to 1,000 Kelvin, which is almost 1,000 degrees Celsius, which when we're talking about Fahrenheit, we're talking about 1,800 degrees or more Fahrenheit. This would melt lead on the top of the planet. So yeah, this is a hot place. So we call them hot Jupiters. Now, when we're looking at the Kepler mission, however, it has another way of registering whether or not planets are going around stars. It's not looking for the wobble and the red shift, blue shift kind of thing. It's looking to see if planets are crossing in front or behind the star and causing it to dim. And this is called the transit and eclipse method along the way. A transit is when it goes in front of the star. An eclipse is when it goes behind the star. So what you've got to have happen here is you've got to be looking at it right edge on. Because if it's going around like this, say my head's the star and it's going around like this, planet's never in front of it, so it never blocks it. Even if it's going around at an angle, it's usually not going to be blocking the star. It has to be right edge on. And that's very rare, because even in our own solar system, we might think that Venus and Mercury being inside between us and the sun would always go in front of the sun. That is not the case. It only happens every once in a while, with Venus only a couple of times a century. So yeah, you've got to get this right on, especially the further away it is, the more precise that has to be. But Kepler could do this. The Kepler mission could do this. And what happens is it could measure up to not 1/100th or 1/10 or 1/100th, but we're getting into the 8,000ths of the dimming of the star when something goes in front. Your typical television will flicker more than that, and your eye doesn't even pick up on it. Now, the Kepler mission was just deactivated about a year and a half ago. So we're at the end of its mission life. It lasted for more than 10 years, and that was a really good run, considering it was only supposed to last for about 3 or 4 years from its original mission. But it found 4,500 potential candidates. We are continuing to work on the data from Kepler, and that'll probably go up, and we'll probably have thousands of verified planets just from Kepler. But let me go back here when we're looking at this method here. Notice here in our little graphic here, if you're looking at the planet off to the side, and let's say my head is the star and this is the planet, planet's off to the side like it is here in your little graphic, you're getting light from the planet and light from the star. So that's going to be position 1 here on our light curve. But as it goes in front of the star, notice it dips down, because now not only are you not getting light from the star, but this is the dark side of the planet. See, it's the other side of the planet that's illuminated. The dark side of the planet's there. So you're not getting the light from the planet anymore, and you're not getting light from the star. It's dipped until it goes all the way across and then emerges on the other side. Now you're getting full light from the star, and as it goes through here over on the fore side, you're getting light from the planet again. Then when the planet goes behind the star, you get a dip in the light again, but not as much of a dip. So during the eclipse, you're still getting the full light from the star, but no light from the planet. During a transit, you're getting no light from the planet and less light from the star. So it's a double dip, but it's a double dip that are different intensities. And that's what tells us it's a planet going around and not another star. If it were another star going around, we'd still be getting light from the second star, because stars are lit on all sides. Now, we can look for other ways of hunting for planets. One is called gravitational lensing. When you've got something between what you're looking at and your observation, sometimes the light will bend around it, and that can act as a magnifier. So that's helpful in some cases, but again, you've got to have the alignment just right. And then sometimes we can look for dust disks as planets are forming, and we can see the clumpiness that will tell us that there are planets in there along the way. We can measure the orbital period, how long is a year. We can measure the distance from the star. We can measure whether it's going around in a circle or an oval or a cigar shape. We can measure how big the planet is, the mass. We can measure the size, if it's volume, so we can tell whether it's a Saturn kind of planet or a Venus kind of planet. And the density, we can tell, and that will tell us whether it's largely a gas giant or has rock and dust and other kinds of things. And sometimes we can get atmospheric properties from it as well. So Doppler shifts, that sort of back and forth, red tug and blue tug kind of stuff going on, can give us indications as to whether it's cigar shaped or circular, and also the orbital speed. When we've got a tilt going on, we can still get the tug and pull back and forth, but that messes up our data a little bit because it's not precise. It's not as precise if it were edge on or face on. So we have to apply different kinds of math when we've got a tilt. And the thing is, most of them are tilted because most of them are not going to be edge on or face on. Those are sort of lucky examples. But the TRAPPIST system, which is what I've got behind me here, is one of the more interesting ones that we found in the not too distant past, in the last couple of years, actually. And we have found 7 different planets that are here. And we are seeing 7 planets, one of which goes around in less than 2 days, its star. Now, again, that's not unheard of, because one of the moons of Jupiter goes around its planet in less than 2 days, Io. The outermost planet of these 7 planets, however, goes around in only about 19 days. And they are all close enough to the star that they would not actually even reach out to Mercury. So here's a sort of blow up of what I've got behind me here. Notice here's our solar system with the Sun, Mercury, Venus, Earth, Mars. Notice this is times 25 here. So all of these planets and its star, the TRAPPIST-1 star, would fit within our inner solar system. But not only that, they fit within the orbit of Mercury. Mercury takes 88 days. Venus takes 225 days, Earth takes 365 days. This planet H, and then we've got one that's just a little bit off the screen over here. I'm sorry about that. I takes 19 days. Now notice here also, the closer you are into the star, the hotter it is. But then you reach this Goldilocks zone, this green zone here. This is where life could exist. Venus is just beyond that in the hot zone, but once upon a time when the sun was a little dimmer, it might have been in the habitable zone. Earth is clearly in the habitable zone. Mars is just inside the habitable zone too. Notice we've got several planets here that are inside the habitable zone, even though they're closer to the star. That's because the star is dimmer and it's not as hot. If you've got a dimmer star, the habitable zone is closer. If you've got a hotter star, the habitable zone is further out. So that's something to watch for when we're looking at these things. We can calculate the density of planets, which tells us whether it's a gas giant, whether it's a rocky planet, whether it's going to be mostly water, water world, or mostly an iron ball. We can tell the mass from how things are going around with the Doppler method, and we can tell the volume, especially if we've got an edge on, by how much it's dimming the light from the star. So we put that together, and that gives us a density. Now, if we are really lucky and we get it on that edge on thing, what we can do is sometimes get the atmosphere. We can tell whether there's water vapor there. We can tell whether there's oxygen there. And that's because imagine my head is now the Earth, not the sun. And light is coming from the sun to the Earth. Well, if it hits here, it just stops. But some of the sunlight will hit right on the edges and continue out into space, having gone through our atmosphere. That, in part, is what turns the moon red during our lunar eclipses. But that light going through, if there was a telescope on the other side, could measure, the sun, and then measure the light coming off of the atmosphere from the sun, subtract the sun, and then say, ta-da, that's what's in the atmosphere. And you could measure nitrogen, oxygen, water vapor, a little bit of other trace elements that are in there along the way, carbon dioxide. That is something that we can do. Again, if we get edge on, you take a reading from the star, take a reading from the star with the planet in front, and then subtract the star, and that tells us what's left in the atmosphere. So every now and then you may see news reports that say this planet can support life, or this planet has water, or this planet has water vapor, or this planet has oxygen. This is one of the ways in which we know that. If they say it can support life, that's a little bit of a stretch. That's an optimistic assessment. If they say they've detected water vapor, that's usually pretty good science. So one of the things that we can do when we're looking at these things is we can do a temperature map. We can do a temperature map of the surface of the planet. We can do especially when it's on the side, or when it's on the far side of the sun about to go into the eclipse mode. And we can tell where the real heat is. We can tell where, and most planets will do this. They'll have a cooler polar region and a hotter equatorial region. all things being equal. But then when we've got atmospheres, that redistributes the heat. When we've got odd tilts, that will change things too. So being able to measure this makes a difference. When we're looking at our extrasolar planets, exoplanets are what they are. Extrasolar means outside of our solar system. We want to compare them to what's happening in our solar system. Here's orbital period, which means how long is a year in terms of number of days. Notice we've got a bunch of planets that whip around their planet in less than 1 day. We've got a bunch here that go around in 10 days or so. We've got a bunch here that go around between 10 and 100 days. Earth is going around in 365 days along the way. Why are there so many over here? Well, here's the thing. It's not that there are more like this. Those are just easier to find. It's easier to see a star doing this, back and forth, back and forth, back and forth, than it is to see a star doing back and forth, back and forth. So yeah, it makes sense that these are the ones we're going to see, the ones that are moving faster. We have a lot that are closer in than our planets, but again, the closer they are, the more of a wobble they're going to give to their star. Planets that are having that are larger as well will be easier to detect. So that's one of the things that happens as well. Planets that are farther away from their star are harder to get that Doppler effect going there. So most of the Kepler planets are what we would call either Earths, super Earths, or mini Neptunes. So they are Earth-like planets, as you can see, quite a number of those. And then we've got our Neptune, so gas giants, but not too much larger than the Earth, not anywhere near sort of the kind of Neptune and Jupiter kinds of planets along the way. So you can see by far Kepler, looking edge on for that transit and eclipse, that brightness dimming kind of thing, found a lot of Earth-like planets, and that's encouraging to us. We're not as likely to find those in the wobble effect or even the Doppler effect along the way. So some things that are surprising to us, there's a large diversity of planets out there. There are a lot that are in more cigar-shaped kinds of things. That's not so good for life, because if you're trying to stay in a habitable zone, the habitable zone is always going to be circular. So if you're going in a cigar shape, you're going in and out, you're going where it's too hot, too cold, too hot, too cold every year. And that's going to mess up the system. And then we've got these hot Jupiters, which I've mentioned before, which are really weird because they should have boiled away, or at least that's what we used to think along the way. But then as we assess different kinds of ways in which planets form, remember we've talked about these sort of gas and dust clouds where planets are forming inside of protostar systems. We have various twisting forces, we've got various nudges and other kinds of things that are happening as the gases and dust coalesce. And we've got lots of different pieces and particles and planetesimals that are hitting each other along the way. So that can cause sometimes planets to migrate in or migrate out. So one of the theories is that planetary migration has pulled in these Jupiter-type planets into where the stars are after they formed outside in an outer part of the solar system. And one of the interesting things is people are looking at our own solar system and wondering if Jupiter used to be closer to the sun. They're looking at whether Uranus and Neptune used to actually be swapped in different places. Planetary migration may be a thing not just for these other planets, but for our own. So as we look at these different ways in which gravity interacts with a forming star and forming planets, inward migration is an interesting effect that happens. So another thing that can happen is lots of stars form as parts of clusters. So a star over here could actually exert a little bit of gravity pull, and that could throw things off from being a perfect circle. Also, if you've got two really big planets and they're not in perfect circles, they can start to interact with each other along the way. And you may have noticed a little bit of that when you were doing a lab. if you've done the lab with the Colorado simulations. When you have two stars and a planet, sometimes they'll collide, and that becomes an interesting thing. We also can have resonances where you have them like the 3 moons of Jupiter, always going in a cycle, where one is going 4 times a week, another is 2 times a week, and one is 1 time a week, and they're always going in that pattern. That's called a resonance. Some of the TRAPPIST and Kepler kinds of planetary discoveries are in resonances like that too. So we're modifying our nebular theory. We're trying to figure out what all this means. This is one of the values of looking at things outside our solar system, because it helps us to understand our own solar system better. But of course, one of the things it's done is confused us tremendously. We didn't know what we thought we knew. And that's one of the great things about science, is you can come up with things that explain things, but they may be incomplete. You may know how to cure part of something, but not the whole thing. You may know how to explain part of something, but not the whole thing. Now, just because our information is incomplete doesn't mean we don't know anything. Just because our information is incomplete doesn't mean we don't have enough to work with. Most people do not know how airplanes actually fly or how engines actually run. And yet they get on the plane and trust that the engine's going to run and the airplane's going to fly. You don't always need complete information. What you need is enough information to explain and do what you need to do. That's something that's important to remember in our current environment when people are debating about science of different kinds of things to do with our pandemic. That's an important thing to remember. Just because science isn't complete doesn't mean it's wrong. And that's been true all along. So when we look at these different kinds of planetary systems that are out there, we see that there may be as many as 20% of the stars that have Earth-like planets where they're actually in habitable zones. They're in the green zones. That's great for us because there are lots and lots and lots of stars out there. So even 20% still means there's lots and lots of stars with Earth-like planets that we might one day find life on along the way. And some of the things that we're hoping to use to continue that, I've talked about the Gaia mission and the Kepler mission, the TESS mission. And some of you may actually see some of this on a project called Zooniverse. If you ever go online and sort of work with science as a volunteer, there's a website called Zooniverse, and they get data from the TESS mission where you're looking for transiting and eclipsing stars that are out there. And it is calibrated to pick up where Kepler left off. So the TESS mission is a NASA mission. Then it's going to partner in overlapping ways with the CHEOPS mission from the ESA, which will also be piggybacking onto some of the Kepler mission data as well to measure properties of stars and planets that are in this transit and eclipse mode. Now, of course, the Holy Grail is, can we just take an actual picture? This is an actual picture from the European Southern Very Large Telescope, which is down in Chile in the Atacama Desert area here. And what they've done is they blotted out the central star. They've sort of put something there so it doesn't overpower it. And we can see, we're looking at it edge on, we can see a disk of debris that is forming planets along the way. When we get the James Webb Space Telescope, it'll be a lot more powerful than the Hubble, and it will be able to help us take pictures like this too. This one is from the Large Binocular Telescope, and it shows several potential planets around a mostly blocked out star. And this is a pretty dim star to begin with. The TRAPPIST star is also a pretty dim star. If we're going to get really good pictures like this for at least the next couple of decades, they're going to be from dim stars where it's not so overpowering you can't see. We're never going to see planets around Betelgeuse in the next 10 to 20 years, for example, because Betelgeuse is just too bright. We're not going to see planets around Sirius in the next 10 to 20 years because they're just too bright. After 20 years, depending on technology, I'm not going to say we'll never be able to see them, but in the next 10 to 20 years, yeah, this is what we're going to see though. But this is so much more than we could have even when I was taking this course. Because remember, when I was taking this course, they said, we have no idea whether any star has planets other than our own. And ta-da, now we're discovering that maybe as many as half the stars that are out there have a planet or two, or 9, or 12. We don't know. So there's still areas that we don't know. So that's it for our exoplanets. I do get excited when I'm talking about this topic because, again, it's all new. It's all brand new. I read an entire book on exoplanets just last summer, which was quite something. And there's a service called Coursera, or maybe, yeah, no, it's called FutureLearn. And FutureLearn actually teaches a course just devoted to exoplanets, and I took that as well. And you get to look at many of the programs that are being used to decipher the data, and you get to look at what we've got on the TRAPPIST system, like we have up here, or various other Kepler systems that are out there. So again, thank you for joining me on our trek a little bit outside of the solar system. Our next and final lecture for this class will go to the heart of the solar system. We'll be looking at the sun. Get your sun goggles ready.